Okay, so welcome to our presentation on our paper that was published at NeurIPS 2025 called LookWhere, Efficient Visual Recognition by Learning Where to Look and What to See from Self-Supervision. Here is myself on the right and Evan on the left presenting LookWhere poster last week at NeurIPS. Speaking of which, I am quite sick right now and I got sick from NeurIPS, so you'll have to bear with me. I might be sneezing and coughing throughout. Okay, this is work that was co-led by myself and Yousef will help me present a lot today. We got help from Jin Fang, Daniel, Tarek, and then co-last authors are Jim and Evan at Carleton University, UBC, both at Canada, and Vector Institute, also in Canada. Okay, so some introductions to start. I'm a third/final year PhD student at Carleton, supervised by Jim and Evan. And my topics are self-supervised learning for efficient transfer, compute efficiency via architecture, adaptive compute, and this work would fall under this category, adaptive compute, and remote sensing is a specific application. And like I said, I'm currently sick. I caught something at NeurIPS.
All right, and my name is Yousef. I'm a second and final year master's student at Carleton University, supervised by Jin Fang Wen. And I've mostly focused on self-supervised learning, reinforcement learning, and specifically reinforcement learning for discrete algorithms and discrete optimization. So jumping into our presentation on LookWhere, to give you kind of the big picture, high resolution imagery, so imagery where we have 1,000 pixels on each side has become very common in the real world. So specifically in photography, remote sensing, and satellite imagery, autonomous driving, medical imaging, and many more areas, especially as cameras have improved over the years. You have cameras that are powerful enough to give you high resolution on phones these days. And these images at high resolution are specifically useful for computer vision models, because they give very useful detail and context that can inform these models to make more informed predictions that improve performance. However, this performance comes at a cost. So when you're processing high resolution, you have lots of pixels. Obviously, when you're processing an image that big, it costs a lot more than when you're processing a lower resolution image. So the performance increase doesn't come for free. Fortunately, lots of images exhibit spatial redundancy. So to understand what the image contains, humans don't have to process all the pixels. They don't have to look at the whole thing. There's usually a smaller subset of pixels or a smaller subset of the image that contains the information that's required to understand what that image represents. So our goal with this work is to train a model that's capable of identifying this subset of informative patches, which we'll show later is a very small subset in some cases, like even just 10% of the image is sufficient. And we want to process only what matters in order to improve the efficiency of our models. But importantly, we want to process it at high resolution because we want to take advantage of that detail and context that is lost when we downscale the image to lower resolutions. So step one of this is to identify where to look for this important what. And that's basically where we're going to start with LookWhere.
Okay, so we first need some background on vision transformers. And so, excuse me. So the vision transformer is very popular. It's been, excuse me, it's been cited 75,000 times. Sorry. It's state-of-the-art for many applications and foundations, especially when leveraged with SSL, which is self-supervised learning. And so like the typical recipe is to instantiate a VIT, vision transformer, collect a bunch of data, do self-supervised learning for as long as you possibly can, and then kind of adapt it to your downstream task. And this has been done with quite some success, for example, with 3D vision, with Duster, image generation with diffusion transformers, segmentation with SAM, and 2D vision with Dino, V2, V3, Franca, etc. It's also general, so it can be extended to time series, 3D point clouds, video, etc. So next, let me explain how a VIT works. So we take an image and we slice it up into a bunch of patches. Now, once we have this grid of patches, in this case, this is a 3x3 grid of patches, we can flatten this grid into a sequence. And then individually, we can project that patch of pixel values to a patch embedding by first flattening the patch and then sending it through a linear projector or a linear layer. And this linear layer is shared across all the tokens. Afterwards, we prepend a CLS token, which contains global information, or at least we want it to contain global information, because we're eventually going to use that for classifying the whole image rather than just a single patch. Excuse me. And we will add position embeddings to these patch embeddings, and these position embeddings represent the original position of the patch within the image. For example, the position embedding 1 right here is going to be a learnable embedding that contains the information I'm in the top left kind of thing. And so when we add the information I'm in the top left to the patch embedding, or these actual pixels, then it fully contains the information such that the vision transformer can process the image. If we didn't have these positions, then the VIT would just get a bag of patches. And so next, what we do is we just send the sequence of tokens. A token is a general term for a vector input of a transformer, which includes all patch tokens and the CLS token, and potentially register tokens that we'll introduce in a few minutes. So we're going to process that with just a vanilla transformer that was invented a handful of years ago that I'm sure everybody is very familiar with. And then if we want to do classification, for example, if we want to predict if this is a bird, a ball, a car, that is the dominant object in the image, then we can send that final CLS representation through either a linear head that classifies it or an MLP that spits out these logits that correspond to class predictions. Now, inside of a transformer encoder, there's kind of two main ingredients here, two main sublayers. One is the multi-headed self-attention that is essentially between token processing, right? So it moves information between the tokens to allow the transformer to spatially reason. And then we have an MLP, which is also called an FFN, which does within token processing. And so attention is pairwise computation. Attention maps are n by n similarity scores. And we have, for each head that we have, attention head that we have another n by n similarity score map. And different heads have, of course, different pairwise computations. And Yousef is going to explain that in more detail in the next few slides. And these MLPs/FFNs are shared across all the tokens, and they offer token-wise computation. And so the amount of computation scales linearly in the number of tokens for the MLP/FFN and quadratically for attention. Although VITs are amazing and used everywhere, they are not efficient enough for all uses. So for example, in high resolutions, which are common in remote sensing, biomedical imaging, and many more applications, and for high speeds, for example, that are crucial for time-sensitive applications, for example, self-driving.
All right, so Anthony mentioned attention, and attention is going to be a central theme of how we identify the visually interesting areas that we want to process in LookWhere. So it's worth diving into more detail into how attention works and kind of understanding what this attention map represents. So as Anthony mentioned, the way that a vision transformer works is it's going to divide an image into various patches, and a patch contains several pixels. So it's basically just an area of the larger image. So for sake of example, we have an image of the car on the left here, and we're dividing it into a 3x3 patched image. So we've labeled these patches based on their coordinates. So 0, 0 in the top left, all the way to 2, 2 on the bottom right. And we'll walk through basically how attention works so that you kind of get an intuitive feel for what it's doing. So as Anthony mentioned, each patch is going to be flattened and projected into a very low level representation. So that represents the kind of the low level pixel-based contents of that patch. And as it undergoes processing in various transformer layers, which contains multi-headed self-attention, and then projection through an MLP, each patch representation slowly gains more information until it becomes a highly semantic representation of the patch, taking into account the context within the broader image at the end. So that's what we hope that the transformer outputs. So specifically on this slide, we're going to focus on the self-attention feature. So this is going to happen multiple times in different heads. So you're going to take the patch representation, divide it up, and do this computation several times, and then connect those outputs at the end. That part is not really important for us. So we're just going to focus on the computation of one head and what it's doing. Effectively, each patch token is going to be projected via a simple linear layer into 3 different types of tokens, which we call a query, a key, and a value. Intuitively, the value is what represents the contents within that patch. And the goal here is for each patch to take into account the values or the contents of other patches and perform some computation in order to gain a more informative representation for that patch itself. So the way we do this, so just taking an example, looking at patch 1.1, if we say that that's the second patch token that we're processing, so Q2 in this case, the way we're going to mix values is we're going to compute a score for Q2 or patch 1.1 with all other patches in the image. And the way we do this is we just perform a dot product between the query, so Q2, and the keys of all other patches, so K1, K2, K3, and that gives us attention scores, A21, A22, A23. And intuitively, so dot products are larger when vectors are more similar. So if you have a query that's more similar to a key, then the attention score is going to be larger. And the way we're going to use these attention scores is we're going to normalize them, get weights, and multiply these weights by the values, and then sum these weighted value vectors to get a output of this attention layer, which is represented at the top in pink, x1, x2, x3. So effectively, you can look at self-attention as a mixing of all these patch value tokens in order to get a new value token weighted by patch A's attention scores to all other patches. So the higher the attention, the more that a patch attends to another patch, the more contribution that patch will have in the next layer. So the intuition here, or the parts, like the main takeaway, is that attention is serving as a mechanism to identify what's visually interesting in the image. If a patch receives high attention, then it contributes more to the next layer and the final representation. And if it receives low attention, for example, in the extreme case, if the attention is 0, so both vectors are orthogonal and they're totally not similar, then the weight is going to be 0. Multiplying 0 by the value vector of the patch that's contributing to the next layer basically eliminates that patch. And so it's not even important to the next layer or to the final computation. So we asked the question, can we identify this quickly? So instead of doing all this computation to get this attention matrix, which at high resolution is very costly, can we do this quickly, identify the patches that receive low attention, and simply remove them? Because if they're not important to the computation, removing them early should not affect the final output in a meaningful way.
Okay, great. And I should note that these patches are gigantic, just to kind of show off how attention works, where in modern vision transformers, the patch size is like 14 to 16 pixels by 14 to 16 pixels each, instead of these gigantic patches. And so, for example, Dino V2 and Franca, which are 2 common visual foundation models, their default resolution is 518 by 518 images, which means there's actually 1369 patches per image. And so the attention matrix is 1369 by 1369, and then we have additional CLS tokens and registers. And so these attention matrices are truly gigantic.
And just jumping in here, we're going back to the slide for 1 second. So that's how attention works at the patch level. So as Anthony mentioned, we have we can add additional tokens that don't necessarily represent patches. So for example, if you look at the attention matrix at the top left, you'll see a CLS token. So this is just an added token that the transformer itself can learn. And the CLS token can attend to all other patches. And the purpose or the goal here is that the attention token is going to aggregate information at each layer from all other patches to get a more global view of the image or global context. And at the same time, all other patches can also attend to the CLS token to perform computations with that global context. And more recently, several state-of-the-art architectures have introduced registers as basically other forms of the CLS token to aggregate global information or store information that is used in intermediate computations for the transformer.
Okay, and I do see that other people have joined the call, so just an apology that I did get quite sick at NeurIP, so please bear with us. Okay, so I guess most people are familiar with CNN's convolutional neural networks, and so let's just quickly kind of summarize the key differences. So VITs are non-hierarchical, which means that the feature map after patchification, and I'll go back and say that this stage right here, people call it tokenization or patchification. So this is patchification. So the feature map after patchification has the same shape as the final feature map, which is going to be batch size by the number of tokens by the dimension of each token. So CNNs increase the channel dimension, but decrease the spatial dimension via pooling. Now, VITs offer sparse computation. Since VITs are attention only and non-hierarchical, patches can be easily dropped. And implementation is trivial. It's just one line of code. You just index from your tensor. It's very, very easy to do. And fewer flops actually translates into higher throughputs without needing any sort of fancy sparse computational kernels. And when I say patches are dropped, it literally means that the model just processes the VIT as if that token were not there. It doesn't have to process it all. It doesn't get like a mask token and then it's fed through it anyway, like we saw with masking in NLP, for example, with BERT, where BERT, you give it a mask token and that token still stays in the network, still stays in the input sequence. Here, when we say patches are dropped, we literally mean we remove it from the input sequence, the input set. And so VITs also have attention maps, which Yousef just explained. And we have, these are matrices of pairwise similarity scores of shape n by n, or n plus the number of global tokens times n plus the number of global tokens, where n is the number of, in what I just said, and n is the number of image patches. And these move or mix intermediate representations between the tokens for spatial processing.
All right, so introducing LookWhere. So once again, to reiterate, our goal is, instead of processing all the regions or all the patches of a high resolution image, so the high resolution, if you keep the same patch resolution, so the same amount of pixels per patch, higher resolution means more patches means more computation, and it scales quadratically by resolution or linearly by number of patches for a transformer. So high resolution is very expensive to compute. Our goal here is to quickly select the interesting regions of an image and only process those. That's going to be very cheap. So how we identify those interesting regions, our insight is that some models, a lot of state-of-the-art self-supervised models such as Dino V2 or Franca, already identify these important regions via their attention maps. So at the bottom here, you can see two images. On the left, we have Parliament Hill. So the important region, or what's important to this image in terms of understanding the image, is the building, which is the Parliament building. The sky is not really important, and you can see that in the attention map, the transformer model here already identifies what's important. So the area in orange and in red is receiving high attention. The areas in dark blue are receiving low attention. So we already have the where. We just want to extract this in order to perform our adaptive computation. Similarly, on the right, we have a rainforest with some birds. The important part of this image are the birds, not necessarily the rainforest itself, or not necessarily all the patches that contain the rainforest. And again, the teacher model is successfully identifying or paying attention to the birds and not the background. So our insight is we can distill not just the outputs of these models, which is their patch representations at the final layer, but also their attention maps in order to perform adaptive computation by learning to make a shallow prediction of where they're performing attention in order to teach our model where to look or which patches are the most important for subsequent processing. So our plan is to use a self-supervised teacher such as Dino V2 or V3 or Franca, specifically using the attention maps to inform where we should be looking, which high resolution patches we should be processing, and then training our model to predict the highly semantic representations that these models produce for those patches, and that's informing our model what to see from those patches. So despite what we just talked about, where intuitively attention is seen as this mechanism that routes or mixes information from patches between layers, and intuitively you can think of it as paying attention to the more informative patches. So you would expect that more informative patches get higher attention scores, and that's at the end kind of forms a segmentation mask for the important regions of an image. Unfortunately, empirically, not all attention maps can inform selection. So just solving a pre-training task, which is what self-supervised models tend to do, does not necessarily necessitate learning attention maps that can be used as patch selectors. In reality, attention maps can usually be noisy, and in that case, they're not super interpretable or semantic. So you can see some examples in the figure here below. So specifically, D3, OpenClip, and some versions of Dino V2 contain these artifacts, so very specific patches that receive high attention. But when you look at the original image, you can't really tell why these patches are receiving high attention. One theory, which was presented in a later paper that we'll talk about in a second, is that some non-informative patches are just co-opted by the transformer to store global information. So they're being used as kind of a pseudo CLS token. And this global information or intermediate information is being used basically as a storage place for subsequent processing in future layers. So it's basically being used as a scratch pad. But the patches themselves at these locations are not necessarily important for the representation.
And just to give an example, so imagine that we're going to select the patches using this Dino V2 gigantic model. We'd have these three, this one, and then these three, and it would completely miss everything interesting that's happening in the image. And so if the input to our model is literally just those 7 patches, then it wouldn't, clearly our model would not be able to represent what's in the image. And so if we use this to guide selection, then this would not work.
So more recently, so in 2024, some research came out introducing registers, which are similar to CLS tokens. So these are learnable tokens that you inject into the transformer. They don't represent patches. They're simply places that the transformer can use to gather information from all other patches, and for all other patches to attend to basically, if these registers are storing global information, those patches can use them as context to serve subsequent processing. When these registers are introduced, we see that these artifacts, which were being used as registers, tend to be reduced because the registers take their place. And so these registers, which are serving as extra learnable tokens, they serve as the scratch pads. And so we get a more semantic image when we look at the attention that the patches perform, because the models are making fewer pseudo global / CLS tokens that are co-opting the patch representations as register tokens. And this gives us more semantic attention maps that identify or pay more attention to the actual interesting or visually interesting parts of the image that we want to identify for subsequent processing. However, I do want to note that you don't necessarily require registers, so they're not a necessary part in order for LookWhere to work. For example, Franca is a model that was introduced this summer, and it learns semantic attention maps that in some cases are even better than Dino V2 with registers. And specifically, Franca does this without using registers at all. So other modifications to the training recipe or alterations to how the architecture is formed can also produce semantic attention maps without the use of registers, and is still an area of active research. But as attention maps improve, or as we learn how to create more semantic attention maps, then this will simply improve the model that we're about to talk about. So jumping into more detail on how LookWhere works. LookWhere as a model consists of two primary submodels, so a selector and an extractor. The idea is that the selector is going to identify where to look in an image. So it's going to produce a selector map. At the regions that are very important, the selector map is going to have high scores. These are patches that we do want to process in subsequent layers. And in areas that are not informative or not super important to understanding what the image contains, they will contain low scores. So we'll perform a top K operation. So we'll simply take the K patches with the largest scores. This will give us a sparse high resolution image with the most informative regions. We'll feed this to an extractor, and the extractor will process this sparse image containing much less patches. So it does this very cheaply in order to get a representation of the high resolution image without seeing the full image. So specifically, we're going to train the selector. So at train time, so those are the two components that LookWhere consists of. When training, we introduce a third component, which is a self-supervised teacher. So the teacher has already been trained in a self-supervised manner to process high-resolution images and extract all the information out of those images by performing a deep computation. So it produces an attention map that identifies the important regions of an image to look at, and it produces an informative and semantic patch representation for each of the patches that it processes. So by performing one forward pass of the teacher, we can get both this attention map and the informative representations for each patch. And we can train the selector by conditioning on a downscaled image of the high resolution image. So the selector can process this downscaled image at low resolution in a cheap manner. We can make the selector predict what the teacher or the attention map that the teacher would output, and we can do this cheaply. And specifically, we use the last layer attention map of the teacher. So the selector does this to identify where. And we can then take the selector map, get a sparse high-resolution image, feed that to the extractor, and specifically for those high-resolution patches that were extracted, we can distill the representations of those patches with the representations of the teacher outputs, and as well as the CLS or global representation of the image that the extractor produces. We can distill that with the teacher as well. At fine-tuning time, so once we've trained the selector-extractor architecture, we can remove the teacher. So the selector receives a low-resolution image, identifies the regions of the high-resolution image to process, gets those regions via top K operation, feeds them to the extractor, extractor outputs representation. We can simply fine-tune that loop, which happens very quickly because the selector, again, processing a smaller version of the image, very cheap. Extractor is processing a sparse version of the image, also very cheap. So we can simply fine-tune that end-to-end for a downstream task, which we'll show in a few slides. And we can do so very efficiently, but gain performance similar to the self-supervised teacher, which was processing the full high-resolution image, because we're only discarding the non-informative parts of the image, which did not contribute to the computation in the first place.
And you can kind of think of our LookWhere as approximating a visual self-supervised model. And so the approximation comes because our selector is extremely lightweight. And it's lightweight for two reasons. One is because it gets this very low-res image, and a low-res image just will have far fewer patches. So, you know, if our downsampled image is like 100 by 100, then maybe it has, 20 patches, and 20 patches is very small. And then we can also use a small model. So, for example, our selector that we choose in our paper actually only has 3 layers. And so compared to any, like a VIT-B, the selector is essentially instantaneous. It's very, very fast. And that'll output the selector map, which then we take top K and give it to the extractor. And the extractor is a full VIT, and so it has this capacity. But it's very fast, and it's fast because it takes this sparse subset of high-res patches, for example, 100, 200 patches, instead of the full 1369 high-res patches that the teacher processes. And again, we discard this teacher after pre-training, and so fine-tuning inference is extremely quick.
And just one other thing to add, because the selector, even though it's processing a downscaled version of the image, because it's processing the full image, it does have some global context, specifically in its CLS tokens and in its register tokens. So the selector is also a transformer, just a smaller one. So we also use those low resolution global tokens, give those to the extractor. So even though we're discarding a large portion of the high resolution image, we are still giving it the global context that the selector extracted from the downscaled version. And we find that that helps performance.
And so we do have a question that I'll just address here. So one question is which layer and heads attention maps to use? So we do use the last layer attention maps from the self-supervised teacher. We'll get into that more later. And the heads, we just average over all the heads. Then the first question was, would extracting only important patches hinder the extractor's ability to learn the representations of non-important patches since it never sees those? It never learns not to pay much attention to those patches. Yes, although we argue that that is an empirical question, which we will show that, excuse me.
Yeah, so in terms of hindering its performance, so there's two aspects here. One is that if we just want to, for most downstream tasks, those non-important patches they don't really affect the performance on that downstream task. For example, if we want to classify an image, we don't really require the background if there's a central object in that image that actually matters. And we'll show some examples of downstream tasks where that's true. The other part is that if some important feature of the background is actually important for the image, for example, global context, then the selector over here, which is processing the downscaled image and extracting that global context in its global tokens, by feeding that to the extractor, we kind of retain that performance of not processing those background patches, but still containing that information in the global tokens. I don't know, Anthony, if you wanted to add anything.
Yeah, I mean, that's more or less fine. Thanks for bearing with me, by the way. But yeah, like basically what I was trying to say is that it's kind of an empirical question that we'll have to show with downstream tasks, like how much accuracy do we lose by only processing like 10% of the input? I mean, not performance, but ability, like non-important patches could be adversarial attack to the network. So we do have some adversarial attack results. Why don't we kind of go through it, and then if there's still questions, then we can talk about those at the end. Okay, so next slide. So first, we're going to test LookWhere on standard image benchmarks. For example, ImageNet classification and 8020K semantic segmentation. And so these are the gold standards for these tasks in computer vision. So that's why we chose them. And LookWhere outperforms the state-of-the-art adaptive computation methods with regards to the speed accuracy trade-off, which is kind of what most of the papers in this literature cares about. They mainly care about, okay, we're at 75% accuracy, how fast is your model? Or at this speed, how accurate is your model, kind of thing. And we compare it to methods like Pitomi. Pitomi was published at last year's NeurIPS, and it is an improvement on the famous Tomi paper, token merging. There's DTAM, ATC, LTRP, and LookWhere outperforms them all on these two tasks. But next, actually, the next task we're going to talk about are, in my humble opinion, a bit more interesting, and they showcase the LookWhere's potential and speedups more nicely.
Yeah, so the first task, so these are all fine-tuning tasks. So these are all downstream tasks after the pre-training step has been performed. The first downstream task that we look at is detecting speed limits from high-resolution imagery. So we have a data set of a bunch of images on highways and in cities where there's a speed limit sign in the image. And it's important that we process this image at high resolution, because as soon as we downscale, the lower resolution is not going to be or it's not going to be at sufficient fidelity to identify the speed limit in the traffic sign, which is usually a very small portion of the image. But you can see that if we're processing this image at high resolution, so around 1000 by 1000 pixels, the important part for this task, which is identifying the speed limit, is containing a very small portion of the image, so less than 10%. So what we do in our experiments is we take our pre-trained model and we just fine-tune it by fine-tuning the extractor. So the selector is not touched, it's frozen. We process it end-to-end. The selector, we'll show you some maps in a second, usually generalizes and identifies this small section of the high resolution image, which is processed by the extractor in order to predict the speed limit. So if we go to the next slide, you can see some examples of some selector maps. So these are 6 images. You can see the selector map that our selector produces. Again, this is from a lower resolution version of the image. And the region that receives high attention usually, in most cases, contains the traffic sign. And then we use that to extract a high resolution segmentation map, which contains the traffic sign, feed that to our extractor to predict the speed limit in each of these scenes. And we can see that in the next slide. Our performance, so LookWhere here, so we have a few plots. So on the left, we plot throughput, so the speed of processing, so higher throughput means more efficient, against top 1 accuracy, so the accuracy of the top prediction, or the most probable prediction for the speed limit. So you want to be on the top right of this plot. That's the best performing model. And we can see that LookWhere basically achieves the Pareto frontier, the best trade-off between accuracy and efficiency or throughput. So DPS achieves higher throughput, but sacrifices accuracy. IPS achieves slightly higher accuracy, but significantly lower throughput. And the interesting part here is that DynoV2, which was used to pre-train LookWhere, so all of the representation power of LookWhere is initially trained from DynoV2. LookWhere matches, or in some cases exceeds, DynoV2's performance, achieving the same or higher accuracy, but significantly improves performance, which demonstrates that we can drop the majority of the image. In this case, we're only processing 10% of the image without sacrificing accuracy at all. And this is at inference time. LookWhere also benefits from increased efficiency during training because we're using, when we fine tune, we're not using the teacher, we're just using the selector, and that's processing a low resolution image, and then the extractor is only processing a subset of the image. So even at train time, we're very efficient. So you can see that the flops, or the amount of computations used during training compared against the accuracy throughout training, LookWhere does not use any flops or many flops at all, so you can see it in the stars. By not using many flops, it improves accuracy very quickly, whereas the other models consume a lot more flops to train their models fully and achieve similar accuracy. And you can also see on the table on the right, the training cost specifically. LookWhere, if you compare it to DynoV2, and these are very similar models, specifically the extractor for LookWhere is basically the same thing, or initialized from DynoV2, but only processing a subset of the patches. By doing that, we significantly reduce the number of flops, or the amount of computational units that we're using. The memory is also significantly reduced by about 90%, and the speed is significantly increased. And effectively, LookWhere is state-of-the-art in this class of adaptive computational models. So we do similar experiments for 2 other data sets. So the first one is birds or cub. So in this task, we have various images containing various species of birds, around 80 species of different birds. And the task is to identify details or fine-grained details on these birds that will inform the model of the species. So it's a classification task. And once again, the background here is not relevant for the species of bird. So when we're processing a high-resolution image, we don't really care about most of the patches. So even if we segment around 10% or 20% of the high-resolution patches and process those with the extractor, we expect to maintain performance. And you can see that our selector, without even being fine-tuned on this task, successfully identifies the important region of the image which contains the bird. So we'll show that we can maintain classification accuracy. And then perhaps a bit more interesting, on the right, we have a billiard balls task, which was introduced by a similar paper looking at adaptive computation. And the task here usually contains 4 to 9 billiard balls on a table. And each of these balls contains a number that is visible in the image. And the goal here is to look at the rightmost ball and the leftmost ball and output the larger number between them. So again, it's important that we process the image at high resolution, because once we downscale or process at low resolution, the number on the ball is no longer identifiable. So we can see that once again, without any further training after the pre-training stage, our selector map successfully generalizes to this task and identifies the informative regions in the image, which contains the balls. And then once we process these sparse patches, our extractor is successfully able to be fine-tuned to perform this interpatch reasoning to identify the rightmost ball, leftmost ball, which is information contained in the position embeddings of the original model. That's how it knows what is the rightmost and leftmost. And it can route that information between the patches to identify the larger number between the leftmost and the rightmost ball. So if we look at the results on the next slide, we can see similar results to the traffic example, where we're plotting throughput against top one accuracy. So again, LookWhere achieves the Pareto frontier, or the best trade-off between accuracy and throughput, where DPS usually achieves higher throughput, but at significantly lower accuracy. And in most cases, LookWhere is very competitive with state-of-the-art in terms of accuracy as well, but at significantly higher throughput. And again, within the billiard ball example, we basically match our Dino V2, or the teacher, which also suggests that if LookWhere is trained with an alternative teacher, which achieves higher performance, because models improve every single year, that LookWhere automatically gains these benefits. And also in bird classification, we can see a similar thing, where LookWhere basically achieves the same accuracy as state-of-the-art models at higher throughput.
Okay, so yeah, there's a vision transformer actually computes many thousands of attention maps, and so there's a question of which attention map should be the target for the selector. And we show that the last layer of the patches, so where the patches are actually looking, and only at the last layer, achieves the best trade-off between segmentation and classification. We could also use other teachers. So in the summer, we trained a LookWhere version of Franca. It worked very well. We also trained a LookWhere version of MAE. This did not work at all. And this is because MAE, number one, has quite poor extracted features. It needs to be fine-tuned to be useful. And that MAE's attention maps, we tried a bunch of different things, and MAE's attention maps were not useful in our setting. And so LookWhere does need these kind of nice attention maps in Dino V2, Franca, Dino V3. Now, luckily, the state-of-the-art models do typically contain these nice attention maps. We also do an adversarial attack experiment, and we show that LookWhere is actually more than twice as robust to adversarial attack as Dino V2. These are not practical adversarial. We do not claim practical adversarial robustness. This is just an exploratory experiment to encourage further work in this area.
And comparing LookWhere to some other works that focus on using transformers to increase the efficiency of processing high-resolution images, most comparisons are to token merging or dropping methods. So for example, token merging, or TOMI, is a highly cited method that gradually reduces the number of tokens in the representation via merging. So at each layer, they basically take the patch tokens, divide them up into two sets, a set A and B, and they do an assignment between these two sets. Intuitively, the assignment assigns similar patches together. So if you have two patches that represent a very similar thing, then you might as well merge them so that they both can represent that thing. So at each layer, or not necessarily each layer, but progressively, you get a halving of the tokens until at the end, you basically merge all of the regions of the image that represent the same thing into one token. So you can see that in figure A here, where you have regions in the same color. Those are one token representing the same thing. And then dropping is similar, except instead of merging similar tokens, one of those tokens is simply dropped because it's not required, since another token is representing the same thing. The key difference between merging and LookWhere, our method, is number one, the sequence length that is processed. For an image with n patches, when you do merging, you still have to process those n patches for the initial few layers before you do the merging. And the merging is gradual. So you only get the real true benefit of merging once you discarded a large portion of the patches, which usually happens towards the end. So while merging does improve efficiency, it does so very slowly, and you don't really see a large benefit, whereas LookWhere does not do merging at all. It identifies informative regions straight away and drops the non-informative ones. So LookWhere never processes the full sequence length, and it doesn't do a gradual dropping of tokens. It drops all tokens right at the start and only processes the subset through all transformer layers. So we see a much larger increase in efficiency by doing this. The other thing is that LookWhere uses a standard deep learning architecture. So we just feed the subset of patches that are informative to the computation to the architecture, the regular transformer architecture, which happens or can occur very quickly. on GPUs, whereas merging methods have to use that matching algorithm to perform the merging. And that matching algorithm is not necessarily very fast on GPUs. It increases flops. And so even though you're increasing efficiency in one area, you're increasing computation in another, and they tend to cancel out. The last thing to mention is that LookWhere, because it learns or it's trained via a task agnostic teacher, such as Dino V2, which is trained in a self-supervised manner on a variety of, or a large data sets. It learns a task agnostic sparsity, which generalizes to various downstream tasks, as we demonstrated with traffic science, birds, and billiards, whereas Tomy and a lot of related methods are trained in a supervised manner with labels, and they're fine-tuned, so they learn sparsity specific to a task, whereas Dino learns sparse as very general sparsity, and then that can be fine-tuned for a downstream task. But during fine-tuning, you immediately get the benefits of that sparse representation.
And so there's another method, which is patch selection, and now these are one very nice example is patch drop, which uses reinforcement learning. Now, for the sake of time, we won't go through this. But essentially, the discrete optimization is finicky. It requires sampling and careful tuning and multiple complicated stages, which LookWhere sidesteps. So what's next for LookWhere? So next is LookWhen. We're going to extend LookWhere's time through video, which exploits spatiotemporal redundancy for computational savings. And then, so that's it. Thank you. You can find our paper here, and our code and models are released here. We'll take any questions now. Thank you, and thanks for bearing with my voice and struggles.
Yeah, great talk, Anthony and Yousef, and hope you get very soon. So I can start with a question. So is top K, is it a fixed number, or is it like a fixed hyperparameter, or can it like adapt based on how much information the image has?
Right, so it is during pre-training, we vary K from I think like 16 all the way up to 128. And then it is a setting that the user has to select. Our selector doesn't output what it thinks K should be. And so we'll leave it essentially to future work is how to figure out how to train a model that can output the value of K, like what actually K is, but also the selector map itself.
It is worth also mentioning we did perform some experiments that effectively thresholded the attention map. So it's like maybe some regions receive high attention, and by thresholding by K, you leave out high attention regions. Even when we threshold, like we set a logic threshold or attention score threshold to vary K, we don't find that it changes performance that much. So it might be the case that just processing the high K, the highest top K tokens in a fixed manner is sufficient, or it's the case that for a given task, K can be fixed. So maybe between different tasks, you require different Ks, but for a given task, 1 K is sufficient.
Yeah, so it's task dependent. So for example, if we think back to billiard balls, like, you know, maybe 10% is okay, and maybe 20% would be a bit better, but like going from K value, which is 50% of the tokens, to like 90%, presumably that's not going to help at all, because as long as you can capture the most important things for the task, then you're kind of maxing out your performance.
Got it. Thanks.
I think there's a question. So it's how would you envision a selector during pre-training itself for efficient? Here. How would you envision a selector during the pre-training itself?
So I think they're asking, instead of processing the full image with the teacher, processing a subset of the image with the teacher. So one thing to mention is that when we use the teacher and we process the full image, gradients are not flowing through that operation. So the teacher is basically being used in inference mode. So even though it's processing the full image, that can still be fairly efficient. If we wanted to pre-train a selector, one potential method is that you have a selection map similar to those selection methods that we skip through, but you could have a selection map in front of the teacher. in order to select the portion of the high resolution image that the teacher would process. The downside of doing so is then you would have to train that selection map probably in order to use the teacher. And also that would introduce a distribution shift for the teacher itself, because the teacher was trained initially by processing the full resolution image. And if you did introduce that selection map in order to train it, you'd have to flow gradients through the teacher and through the selector. So I'm not sure, even if you did introduce that selection map, you're processing less patches, but because you're doing it in training mode, you might still, you probably would not get the benefits of processing that reduced number of patches. So there might be other ways, but none pop immediately to mind in order to use a selector to process less patches with the teacher and gain more efficiency that way.
Okay, so there's another question. Can the extractor and selector be the same model? So the selector can actually be any model that outputs a saliency or selector map. So for example, actually we use a CNN in during our paper rebuttals during the discussion phase, and it worked very well. The extractor needs to be a VIT. Can the models actually be the same? I would say probably not. Like using the same weights. I mean, maybe they could in theory, but it would just be suboptimal. Like it might save you a tiny bit of memory if the selector and extractor are sharing weights. For example, the selector's first 3 layers have the same weights as the extractor's first 3 layers. I mean, that's technically possible to do, but I think that would just result in a suboptimal selector and extractor.